All right. And now I have been saying this to, there's a couple of things came up over the weekend and maybe a little before the weekend, but we were talking about them in meetings and other things. Um, I guess the first of these is that I hope that both of you and all that are listening are already registered to vote. And if you are, that you are planning to vote, and I guess some of you are from not from your hometown right now and stuff, so I hope you've been able to make provision to uh, do absentee ballot or whatever. My wife and I have already voted because we went down on a Friday because of my health condition, and voted at the courthouse. So you can do that if that's a thing, but please vote, folks. It's not only a right, it's a responsibility. I get so disgusted by hearing people bragging about, well, we had 45% turnout this time. Well, we'll probably have more than that this election, but some elections are less than that. That means 23% of the eligible voters will be deciding who's doing what, okay? Because if only 45% are voting, 23% is a majority, a clear majority. And that's not a democracy. That's not how things should be working. So, folks, please vote. If you're not registered yet, I think you have until something about the 15th or 16th or 19th, sometime like that, to register. Now, Kyle, you're a resident of Georgia, is that right?
Yes, sir.
Okay, I don't know what your deadline is in Georgia, but I know in Alabama it's somewhere within 2 weeks, I would say. So please, please do what you can to vote. Uh, I huge proponent of people voting, so please do that. Second thing that came up, and this was in an email from the academic dean, and this was sort of a surprise to me. They are beginning to make plans to bring classes back to campus in the spring, not on a big scale, but on a small scale. And what they're planning now, I think, is to have certain classes on campus meeting in large lecture rooms where people can socially distance. The instructor is behind the plexiglass thing, so it just seems kind of premature because we still are only about 10% of the population has tested positive and is you know had the disease. That means it's a it's still early. We're still on the upward rise, and it just seems way too early to go back to campus. Now, in my last class, some of the students said, yeah, but they really prefer being back on campus. But then they said, but we don't want you to be back on campus. Well, I'm not going to be in the spring anyway, except to clear out my office and that kind of stuff, turn in my keys. But that's not the reason I'm retiring. I'll be 70 by then, so that's when I think that's a good time to go. But the thing is, I wouldn't be able to anyway because of my health situation. But I, what what bothers me the most is that instructors, if they were to get it now, Kyle, I'm so glad you had a very mild case, but you still wouldn't have been able to be on campus. What was it, 2 weeks?
Yes, sir.
Okay. Just think of an instructor not being able to be on campus for 2 weeks. Now that if they had a mild case, some people, I heard Dr. Michael Sag on the television sometime over the weekend. He's a virologist researcher at UAB, world famous by the way too, although most of his work has been in HIV, not in COVID. But he caught COVID early on. I would say back April or May time frame. Jesus is coming in. Right now, where every three students are here. Okay, um, y'all are well spaced out here. You're doing social distancing. Um, And he said, and here comes Houston. Okay, he breaks the trend here. Glad to see that. Uh, so Houston's here. And he said when he first discovered he had it, he didn't feel too bad. He was tired, had the cough, the headache, I mean, congestion, and stuff like this until about day, I think it was 4 or 5. And suddenly then he said it was awful. And especially at night, he was just hardly felt like he could breathe. And that lasted for, I think, more than a week. So he was, in essence, several weeks before he came back, before he was back to normal. He recovered, but it was not an easy situation at all. And I look at that and think, what do you do if an instructor was in that situation? That means the students are going for potentially a month without an instructor. And it just doesn't seem like it makes sense. I mean, yeah, I would much rather be in classroom with y'all than doing it virtually. Way prefer, okay? However, in these circumstances, this is the best we got in my mind. And I think that for students who need better support, as in, I know a lot of students, a lot of my students, maybe some of you, are having to do this distance learning, virtual learning, over a telephone, over that small screen. That's not ideal. It definitely is not. So I can easily see where some students would need to come on campus, but if they do very careful screening, just like they did for Kyle, taking temperatures and things like this, and because still, if a student gets sick, then you're going to have to be, the instructor's going to have to be still recording and doing things through Zoom. So if they're doing that anyway, why not do that? And then, but let the students come back who need the support, who don't have good Wi-Fi, who don't have good internet service. And I know it's an issue. We live in a place, a pretty good, part of town, you might say, but it has terrible internet service. We're down in a hole, and when this thing started and the infrastructure was really bad, our whole wireless provider went down. I mean, for 2 days. I mean, for the whole area here, it was miserable. So yeah, there's issues with it, but in order to keep continuity, it seems like to me we've got to protect the people who, the classes depend on the instructors being able to teach, and doing that from when we're still on the steep part of the curve, that's I don't know. I just have problems. What are your feelings on it? I know I'd rather be back on campus teaching. I don't care for this at all, but I can't now. What do you feel though? If there are classes being offered, would you want to be on campus, or would you prefer continuing something like what we're doing now? Or if you had to be on campus in a computer lab or something like that, where you had not just a mobile device, but actually a computer that you could be interacting with your class.
I'd rather be in class.
Yeah. Okay, I thought 2 or 3 yes. Is that right?
Yes.
Okay, Jermanuel and Kyle. Okay, okay, campus. Okay. Okay, so just about all of you. I haven't heard from Kira. What did you think, Kira? Yeah, I know. It really is. So, I don't know. Anyway, you may get your wish. I don't know. But there may be some classes that will be on campus in the spring. And I know what you're saying. I would rather be on campus too. But I just would not be able to. If I weren't retiring, I would not be able to be on campus. Not with the disease at the stage it's at, and me at the stage where I'm at. I just couldn't do it. And and you would rather have the instructors on campus too, is what I take it when you say on campus, right?
Yes.
Yeah, that's what I was thought. I'm with you on that. I would prefer it too, but man, um, it's just a bad situation. Like Kara said, there's a lot to think about. All right, any other issues, concerns, problems but you want to bring up before we get going on calculus? Okay, sorry, I didn't mean to take 10 minutes of your tuition dollars here, but we did. Okay, where we left off last time, we're in Chapter 10, conics, which we didn't do, parametric equations, which we have done, 2 sections of that, 10.2 and 10.3, and we're now in polar coordinates, 10.4. Good buddy. Okay, we're on page 722, bottom of the page. We just finished sketching a polar graph that turned out being a rose, a 3-petaled rose, and we're at the bottom of that page. Before we get to the slope and tangent lines, that wasn't the example, but it was anyway, it was after that. At the bottom of the page, using a graphing utility, it says, this is on page 722, to experiment with other rose curves. Note that the rose curves of the form, and I'm going to write this down probably on the whiteboard, I think will probably be best. In case some of you don't have books that you can, let me see, I was using my, okay, I've got to do a little bit of housekeeping here. I was having to charge my phone, and now it's charged, and I'm trying to get it unplugged. Okay. Let me get that taken care of. And then let me get my calculator, which we may be needing my phone, plugged back in, because I was using that in the last class. It's not too far behind, but it's a little bit. Okay. All right. Sorry, I wish I had thought of that before class started, but I didn't. Okay, so let me move the taskbar out of the way and move the whiteboard as far as I can left and up. Okay. All right. Now I'll find my pen here. So here are what they're saying about these rose curves. Okay. If you have your equation, R is equal to, such a pain in the neck, okay, A times the cosine of n theta, or R is equal to A times the sine of n theta. Okay. These are the polar equations that produce these curves, these rose curves. Okay. Now, they show a couple of illustrations here, and for some reason my camera doesn't show anything but one of your blocks here. It used to show me and 4 of you, if there were 4 in the class, and which there are. Now it's not. I'm only seeing one block here, and it's not mine, so I can't see what my camera is showing. But here are a couple of those rose curves. Is that held at a place where you can see them? You see the 5-petaled rose curve and then a 2-petaled rose curve? Can you see that? Yes or no? Okay. Do you see the 2 pedal there? A 4 pedal there? This way? Okay. But I'll try to draw these. I can't. The book's too heavy to hold too long. I've got to find out what I did with my pen. There it is. Okay. What the A does for you here, if I can get my pen to show up somewhere. Come on, pen. Okay, wait. Here comes Laron. Let me get him in before I carry on too much further with that. All right, Laron's here. So now we're only missing Esther and James. Now, unfortunately, I found out way late that Esther is still having difficulties. I don't know what happened exactly. I have some suspicions, but she was not able to get on Blackboard to get into the class because the announcements go through class, through Blackboard. That supposedly they got her on Blackboard, but then she was still not able to get in, and I don't know if they've remedied that situation or not. So I'm recording the classes, and hopefully she can follow up and keep up with us. She has turned in her first test, so she's trying to keep up with the class, but she's having difficulties. So any y'all can do to help her, please do so. The combination of Banner, Blackboard Ultra, and then all the other mess that we have to use as far as infrastructure, wireless and stuff, and I think some people just entered some things wrong. I probably don't need to go into this too much, but she, at the beginning of the term, could not register for the class because Banner wouldn't let her. So she registered for Cal 2 again, which she took this past summer and passed, because she thought it would be easier to do a drop add than it would be to register late. When finally we got that worked out, I didn't know all that was going on then. I think what happened, her Pell Grant had already decided that she wasn't taking the 4-hour course, so I don't know. It just messed up her Pell Grant. It messed up everything. Then it kicked her out for not having paid or something like that. And then it just was. And then Blackboard didn't recognize that she's back in the course. So I don't know. It's a huge mess. But anyway, let's go on from here. What the A stands for here, and I was trying. Oh, there it is. Okay. The A is basically your magnitude. Okay. If you had a circle here, you're drawing these roses inside the circle, A would be the maximum. That would be the maximum radius from the center of the circle to it. So the one they show in the book, where R is equal to 2 sine of 5 theta, okay. Now, the 2 means that the radius of those petals is 2. The maximum you go from the origin is 2. That makes sense. Amplitude, okay? The 5 theta basically guarantees it's a 5-petal rose, okay? So the 5 will tell you basically how many petals. And if you think of this, remember that's the coefficient of your independent variable, and remember the independent variable always goes in the opposite direction. A bigger number is going to make a smaller period, and that means you're going to have more petals on a page. So that would be 5. Okay. Now I say that, but then the next one's a little bit of a contradiction to that. The R is equal to and I put these underneath the wrong one sort of, r is equal to 0.5. Again, that's your amplitude, and it's cosine of 2 theta. Okay, now you would think that would only have 2 lobes on it, but it actually has 4 lobes, and but the amplitude is still 0.5. And if you got your book up and you see that, they don't go into any more detail than that. So this just gives you an idea of kind of what to expect, but sometimes you have to expect the unexpected to show up there. So the second one has 4 petals rather than 2. Usually if you have multiples, it is a multiple of whatever that number is there. Okay, that's way more than we probably should have done with this. Let's move on to back to the PowerPoints, and we'll go back to current slide. Okay, so the next topic here on page 723, and by the way, for those who came in late, we are in chapter 10, parametric equations and polar coordinates. We're in the polar coordinates part, 10.4, polar coordinates and polar graphs. We're now on page 723, top of the page. Slope and tangent lines. Now, we already hit a little bit of this when we were doing parametric equations, and we know that slope is sort of a problem there. With polar, we haven't done that, so let's do that with the polar now. Polar coordinates. To find the slope of a tangent line to a polar graph, consider a differentiable function given by r is equal to f of theta. Okay, so again we're writing r as the, you might say, the dependent variable, theta as the independent variable, a lot like we did our rose curves earlier. Okay, so it's some function of theta. To find the slope in polar form, use the parametric equations. X is equal to r cosine theta. Well, what was our r? F of theta. So that would be f of theta times cosine theta, and that gives you your x value. Your y is r sine theta, which again, you plug in what f of theta is, times sine theta. Now everything on the right hand side is a function of theta. However, you've lost your r, okay, that was from up here, and now you have x's and y's. Okay, well, once you have that, the parametric form of a derivative, if a smooth curve C, now that's a key, it has to be a smooth curve. There can't be any cusps, there can't be any corners, there can't be any discontinuities. It has to be a nice, smooth, rounded curve. Okay, is given by these equations, x equal f of t and y is equal g of t. Now, for some reason, they've gone back to t's here. If I were doing this, I would make those thetas, but they're not. They're leaving it as t. And then the slope of C at xy is, just like we did before, dy dx is equal to dy dt over dx dt, as long as that dx dt is not equal to 0. That was from section 10.3. That's where this came from. Using the parametric form, dy dx, given in 10.7, this one right here, you have now, this time rather than dt's, we're going to do d thetas. So this is your dy d theta, this is your dx d theta, and from what we did before, remember, here is x as a function of theta. Now, it's not f of theta, it's some other function because you already used the symbol f here, but this is strictly a function of theta. Y is strictly a function of theta. Okay? Now, don't worry with the f's. This f is different from the one on the next slide. It's different from this f. Well, no, that is the same as this f. Okay. What I was going to say is different from that f up there. Okay. So this is your function of theta times, this is what we were calling g of t up here, is this thing right here. Yeah, this thing right here. And, well, the whole thing here. And your, what we're calling f of t is this one. Those f's are not the same. But it's dy d theta, which is, I wish they had put this on the same slide. Let me write this down. Y is equal to f of theta times the cosine of theta. That's what we had from the previous slide, right there. I'm sorry, sine theta. I'm sorry, I put cosine. But remember, I found that I can erase. Okay. Sine theta. So if we're doing dy d theta, that's a product rule. Okay. So I'm just going to call it y prime because it's easier to write. Y prime, that prime is with respect to theta, would then be the first f of theta times the derivative of the second, which would be a minus cosine of theta, plus the second times the derivative of the first, that would be f prime of theta, that's the derivative of the first, times the sine of theta. And that's where they get this term here. Similarly, your x was f of theta, not that f, but the one from before, cosine theta. So your x prime, this is with respect to theta, would be positive f of theta because the derivative of cosine, I said them backwards. This is the plus, this is the minus. All right, gag, what's wrong? Derivative of cosine is minus sine. Derivative of sine is positive cosine theta, plus then f prime of theta times the cosine of theta. Okay, now, so that's where these forms come from the product rule, because this was a product of f of theta and a sine theta. So that establishes the next theorem. The slope in polar coordinates, if f is a differentiable function of theta, okay? So here we're talking about not, this is the f from 2 slides ago, okay? It's a differentiable function of theta. Then the slope of the tangent line to the graph r is equal to f of theta, okay? At the point r theta is dy d theta over dx d theta, which is that formula we just came up with. F of theta cosine theta plus f prime of theta sine theta over minus f of theta sine theta plus f prime of theta cosine theta. Provided that this denominator, that entire expression there, is not equal to 0 at the r theta that you're trying to determine. Okay? So, they just did a lobe here. Now remember the spiral of Archimedes, it started out something like this. So if you had something that's starting here and going up to here, and there's your r theta, okay? And if that r can be expressed as a function of theta like this, then the slope of the tangent line would be like this, which would be that numerator over that denominator, okay? It's easy to say, hey, yeah, that's what it is. Let's actually do one. I think, let's see if that, no, okay. From theorem 1011 that we just had up there, you can make the following observations. Solutions to dy d theta equals 0 yield horizontal tangents provided that dx d theta is not 0. Okay, so let's go back here. If dy d theta is 0, that's going to make dy dx equals 0, so that will be your horizontal line, as long as dx d theta is not 0 at the same value. If it is, all bets are off. Okay. Now, number 2, solutions of dx d theta equals 0 yield vertical tangents. called vertical asymptotes, okay, provided that dy d theta is not equal to 0. Okay, so this yields your horizontal tangent as long as dx d theta is not 0. This yields vertical tangents as long as dy d theta is not equal to 0. If the dy d theta and dx d theta are simultaneously 0, no conclusions can be drawn about the tangent line. That's basically what we call an indeterminate form. You can't say this is going to happen. It may happen or it may not happen. Okay, indeterminate form. Okay, no conclusion can be drawn. So here's example 5. Find the horizontal and vertical tangent lines of this right here. R is equal to sine theta. Okay, now, and we're only going to go between theta between 0 and pi. Not going to equal pi. Could equal 0, but not equal pi. Okay, so what was our form then? This is our f of theta. Okay, and remember the horizontal tangent line will be when dy d theta is equal to 0 as long as the x d theta is not. Okay, now what was our dy d theta? Going back to that, dy d theta, if you recall, that was equal, now this is your f of theta, so it would be f of theta, which is sine theta, times derivative of sine theta, which is cosine theta, plus f prime of theta, which is cosine theta, times derivative of cosine theta, which is, have I said that wrong? No, derivative of, okay, not derivative. This is derivative of this, so it would be just sine theta. Okay, sorry. I was getting too many derivatives in there. What does that come up to? That's equal to 2 sine theta cosine theta. And what is that? If you remember your trig identity, that's the sine of 2 theta. Okay? And we want where that's equal to 0. Well, that's equal to 0 when theta is between 0 and pi. The only place that's equal to 0 is, well, one place is certainly where theta is equal to 0. 2 theta would be 0. Sine of 0 is 0. So this would be at theta equal to 0. Now, where else? It would be that at theta equal pi, but you see theta isn't equal pi. It's always less than pi. So this is the one and only place where your horizontal tangent line, okay, theta equals 0. How about vertical tangent lines? Well, okay, time out. We didn't verify that your dx d theta is not 0 there. Well, that's what we're going to do next. So let's do dx d theta. Now remember what dx d theta is. There's your f of theta. It's f of theta, which is sine theta, okay, times derivative of cosine theta, which is a minus sine theta, okay, plus your f prime of theta, which would be cosine squared theta, okay, times, cosine theta, okay, I'm jumping ahead, let me erase that. So used to thinking I can't erase on the screen. Okay, there we go. All right. Cosine theta, that's derivative of sine theta, times x is cosine theta, so that would be cosine squared theta when you did that the second time. Okay. Now, what do we have there? This happens also to be the cosine of 2 theta. Cosine theta minus cosine squared theta minus sine squared theta. Well, where is that equal to 0? Okay. Well, that's equal to 0 when 2 theta is equal to pi halves. Okay, so, yeah. 2 theta is equal to pi halves. Okay, that's equal to 0 at theta equal to pi fourths. But again, it happens when theta is equal to 3/4 pi. Because at 3/4 pi, theta equal 3/4 pi, then 2 will go in the 4 twice, so that would be 3/2 pi, and sure enough, cosine is 0 again there. Now I keep thinking we better have 2 of those for sine, but maybe we don't. Let me think. I go back. When 2 theta is equal to 0, or 2 theta is equal to, oh, I left off one. Also at pi halves. Theta is equal to pi halves. Because 2 times pi halves would be pi. Sine of pi is also 0. The next one doesn't work though. Okay. Because it's not equal to pi. Okay. So here are the 2 places where the numerator is equal to 0. So that's where you have 0 slopes. Here are the 2 places you have vertical slopes. These first two are horizontal slopes. Next 2 are vertical slopes. Okay. Now let's see how the book did. I think I'll have to erase some. Let me erase that. Is this the right one? No, that's the right one. Okay. Begin by writing the equation in parametric form. X is equal to r cosine theta, but your r is sine theta, so that's sine theta cosine theta, and y is equal to r sine theta, which is sine theta, which is sine theta squared. Okay? Now, next differentiate x and y with respect to theta and set each derivative equal to 0. Okay? So let's do that here. Okay? So this would then be, let me write it this way, x, I keep forgetting I can erase. I don't like to come down and I'll erase it all. Yeah, okay. Now, so what this yields, I'll do it this way, dx, here I go again, d theta, okay, is equal to sine times derivative of cosine, that would be minus sine squared theta, plus derivative of sine, cosine, times cosine, cosine squared theta. So that's your dx d theta right there. And that happens to be cosine of 2 theta. Okay. This one, and we didn't do it this way, but we'll do it this way this time, yields you dy d theta. I did it again. Dy d theta is equal to 2 times sine theta times the derivative of sine theta, which is cosine theta, which happens to be the sine of 2 theta, which is exactly what we got. So we differentiated both, set each of those equal to 0, set that equal to 0, set this equal to 0, and this is 0 when 2 theta is equal to pi halves or 3 halves pi. So that's 2 theta, not 2 pi. Goodness gracious. So theta will be pi fourths or 3/4 pi. And both of those are between. Oh, here comes James. Good. We're only missing Esther. I don't know if she's made her way back into the class or not. I hope she gets here and gets here soon. Okay. So, good to see all of you here today. Okay. James, we're in chapter 10. We didn't do the conics part. We're in the parametric equations and polar coordinates. Actually, we've already done parametric equations. That was 10.2 and 10.3. Now we're in the polar coordinates part. That's 10.4. And we're on page 723, example 5. Okay. Now, and we've just found the 2 places where you have horizontal tangents and 2 places where you have vertical tangents. Okay. Now, I'm a little ahead of where the slide is here. We differentiated and set each derivative equal to 0. And, oh, I hadn't done it down here. Set this equal to 0. Where in the world is my pen now? There it is. Okay. Sine is 0 anytime 2 theta is equal to 0 or pi. Okay. So then theta would be 0 or pi halves. Now it would be 0 again at, oh, I did leave one off, didn't I? 3 halves pi. Wouldn't it? Let me think. Yeah, no, the next place it would be 0 would be at 2 theta equal 2 pi, and that would be theta equal pi, and theta isn't equal pi. Okay, so those are the 2 places. Now, what they're going to do is graph this thing. And we didn't do this to begin with because then it would have been patently obvious. Okay, so let's graph this thing. If I can find my pen, where is it? There it is. Okay. Okay. When theta is equal to 0, r is 0. Okay, so you start off right there. When theta equal, say, pi halves, r is equal to 1. So theta equal pi halves would be here, r would be 1. So let's call that 1. Okay. When theta is equal to, let's say, 3 halves pi, no, theta is equal to pi. Okay, wait. Let me start over again. Theta equals 0 would be 0. Theta is equal to, let's do theta equal to pi halves. That's the one we did. Then r is equal to 1. Theta is equal to pi. Then r is 0 again. Okay. Now, we need something in between that. Okay. So let's do theta equal pi quarters. Well, your r then would be root 2 over 2. And you'll just sort of have to take my word for it. It would be right about there somewhere, 0.7. And when theta would be 3/4 pi, then you would be minus no, 3/4 pi, you would be here. Yuck, I hate this thing. Okay, somewhere right around in there. It would be 0.7 again. Basically, if I had drawn this properly, that would make a circle here, sitting on the origin. Okay, you can't tell from my drawing, but if you had done it with lots of points, you would have, with a graphing device, you would have seen that's what it came into. So that's what they're going to do here. Oh, okay, they're going to go back and do what we did. dx d theta is cosine squared theta minus sine squared theta, which is cosine 2 theta, and that's at 0 when theta equal pi fourths or 3/4 pi. We did that. dy d theta is going to be 2 sine theta cosine theta, which is sine of 2 theta, which is 0 when theta is equal to 0 or pi halves. We did that. So the graph has vertical tangent lines when you're at these points. That's that √2/2 pi fourths and √2/2 3/4 pi. Okay? And you have horizontal tangent lines at x equals 0, at theta equals 0 and theta equal pi halves. And they just magically throw it in there and say that comes out being a circle also. I thought they would have to graph a few more points, but they didn't. But this is what you get. Circle sitting on the origin, and that's what it looks like. Horizontal and tangent lines and vertical tangent lines are at those points. Because you see when the dy dx was equal to 0, dy d theta equals 0, dx d theta is not equal to 0, and vice versa. So that does form a circle. Okay. Wow, and that's all they do with it. All right, we'll move on. Example 6. Find the horizontal and vertical tangent lines to the graph of, oh, this is a different one. R is equal to 2 times 1 minus cosine theta, where theta goes from 0 to 2 pi. Not counting 2 pi, but does equal, theta equals 0, but not equal to 2 pi, but goes right up to it. Okay? Well, let's do it, I guess, the way the book does. Your x of theta is equal to r times the cosine of theta, which would be, I kind of hate to do this because I'm afraid it'll mess up, but I'd just as soon multiply that through. 2 minus 2 cosine theta multiplied by cosine theta. So that would be 2 cosine theta minus 2 cosine squared theta. Okay, at least I think that's right. Okay, then we would do our dx d theta, and that would be, I left off a theta here, sorry about that. I'm also losing my voice, sorry about that. Let me see what I can do to get some of this gravelly sound out of here. Alright, sorry. Okay. So the x d theta would equal, if I can find my pen. Come on, where are you, cursor? There you are. Okay. Minus 2 sine theta, because derivative of cosine is minus sine. And then this would be plus, I know that's going to come up a plus, 4 cosine theta times sine theta. Okay, 2 times 2, that gives you the 4. times cosine to the first power times derivative of cosine, which is minus sine, which made that become a plus sine. Okay. Now, you set that equal to 0. Well, to do that, I would factor out a 2 sine theta from both terms. In fact, I think I'd factor out a minus 2 sine theta from both terms. That would leave me a 1 plus 2 cosine theta. Okay, and that's equal to 0. Okay, we know sine theta is equal to 0. You could put the minus 2 in there too, but that's never equal to 0. So it basically depends on where sine theta is equal to 0. Between 0 and 2 pi, that's theta equal to 0, because 0 was included there, and pi. 2 pi it would be again, but it's not equal to 2 pi. Or 1 plus 2 cosine theta equals 0, and that would be, okay, 2 cosine theta is equal to minus 1, and cosine theta is equal to minus 1/2. So where is that true? Where theta is, what theta will produce a cosine theta of negative 1/2. Well, if you think about it, cosine starts at plus 1 when theta is equal to 0, and then it goes down to 0 when theta is equal to pi halves. Then it goes down to minus 1 at theta is equal to 3 halves pi. Well, before you got there, it had to go through minus 1/2, and that would be pi sixth, okay, past your 0 point. And that was at, I just said it and now I'm having trouble remembering it. At theta equal pi halves, and pi 6 past that would be 7/6 pi's, I think it is. Doing this sort of off the top of my head. I think that's at 7/6 pi. But then it comes back up to negative 1, just short of it's 0 again at 3 halves pi. Okay, so pi 6 short of that. 3 halves pi would be, oh boy, how many 6 of a pi? The brain's not working well today. 3 halves pi would be how many 6 of a pi? 9/6 pi. Okay, subtract 1/6 pi from that and you have 8/6 pi, which is that right? I think so. And 8/6 pi would be 4/3 pi. It doesn't seem right, but it's working out that way. I'm not sure I did this one right. Let me go back and do this one same way I did that. That would be at theta equal 1/2 pi, pi over 2, which would be 3/6 pi, and then add one more. No, that would be pi thirds, I think. I don't know where my brain was on that. Wait. No, I'm doing the positive side. Let me draw my graph. Okay. Here's cosine. Starts at 1, goes down to -1. Okay. So it's right here. This is, okay. This is at pi halves. And 1/6 pi plus 3/6 pi is 4/6 pi. That's what I needed to say. And that would be 2/3 pi and 4/3 pi. Okay, let me get my 2/3 pi and 4/3 pi. Yeah. And then, yeah. Yeah, that would be it. I think. Okay, goodness gracious, the old gray cells ain't what they used to be. All right, so there are your 4 potential points where your vertical tangent lines are. Potential. We don't know for sure. Let's do the same for y of theta. And y of theta is going to be this r, which is 2 minus 2 cosine theta times cosine times sine theta. Okay, I'll keep saying cosine. Sine theta. Okay, so this is going to be 2 sine theta minus 2 sine theta cosine theta. Now take the derivative, dy d theta, and that would be minus, no, that would be positive 2 cosine theta. Okay, and here we have a product rule. Okay, so this will be plus 2 sine squared theta. That's when you do 2 times sine theta times derivative of cosine. That would be minus sine. And then you have a minus 2 times cosine times derivative of sine. And that would be minus 2 cosine squared theta. Okay. Now, that's pretty ugly, isn't it? Oh man, that is a mess. Make sure I haven't done something stupid here. Okay, they started with this one, whereas they didn't before. Okay. Yep, that is what they got. 2 times cosine theta minus cosine squared theta plus sine squared theta. Yep. Okay. So what we need to do is get everything in terms of cosine. Okay. And that's fairly easy to do. If I could get my pen to show up again. There it is. Because sine squared is 1 minus cosine squared. That's what sine squared theta is. So let's write this as 2 cosine theta plus 2 minus 2 cosine squared theta minus 2 cosine squared theta. That would make that a 4 cosine squared theta. Okay, let's factor out the 2. They did it to begin with, but I'm going to go and do it now. Okay, 2 times, I'm going to factor out a minus 2, I think, and that would be 2 cosine squared theta minus cosine theta minus 1. Okay, now the question is that factorable? I think so. That would be 2 cosine theta times cosine theta. and then we're going to have a plus or a minus. I don't know which to put where, and they're both going to be 1. So let's see if that works. It'd be 2 cosine squared theta minus 2 cosine theta plus cosine theta is minus cosine theta minus 1. I think that's right. Okay. Now, obviously 2 is not equal to 0. Okay. Did someone else come in? I don't think so. I think it's just my pen getting close to that. Let's just make sure. No. Still missing Esther. Okay. So it's where either one of these two is equal to 0, because that's what we're interested in, is the places where the dy d theta is equal to 0. That's going to give you your horizontal tangent lines. So the first one here, and I'm running out of room, is where cosine theta is equal to minus 1/2. Well, looky here. These places are out of the question then, because cosine theta is minus 1/2 for that one. But the other one is where cosine theta is equal to 1. And where is cosine theta equal to 1? It's at theta equals 0. And that's all, folks. Well, theta equals 0 was one of these two. I can't find my thing, so we have to throw that one away. Okay, so it looks like there's one and only one. Well, there's no place where you have a horizontal tangent line, because the dy d thetas, or at least it's not determinable, and one place where you have a vertical. Let's see if that's what it turns out to be. No. I've got something wrong here. Oh. Okay. So we had the same points as before, 2/3 pi, 4/3 pi, and 0. Okay. And down here we had 0 and, okay, I messed something up there. Okay. So we got the pi, got that one. Then I got pi thirds, and it says cosine is equal to 1/2. That's where I messed something up here. Ah, there it is, I think. Yeah, that should be a minus sign right there. Yeah, sorry about that. So this was a minus sign here, and that makes a plus sign there, and cosine is equal to positive 1/2, and that's true when theta equal pi thirds and pi thirds short of 2 pi be 6/3 pi, 5/3 pi. That's where I've messed up. Sorry about that. So here are the two places where you have vertical tangent lines and pi. 3 places you have vertical tangent lines, and horizontal tangent lines now these are back in play again because they weren't out of play. Sorry about that. So that's still good, and that one's still good. The only one out of play is that one. Okay. And we can't really tell about it yet because both of those are 0, but at cosine theta equal 1. Yeah, well, we're not certain about that one. Okay, so there we found our points. This is getting too messy. Let's erase all this and let's watch how they did it. I think once I made my correction there, we got the same answer. Let y is equal to r sine theta, differentiate with respect to theta. So they started off this way. Last time they started off with x, this time they started with y. I did x. Okay. So that would be 2 times 1 minus cosine theta times sine theta. And when you take the derivative of that, they left a 2 on the outside. And product rule here, first times derivative of the second, that's what you get, plus the second times derivative of the first, which would be that then. And that basically turns out the same thing we did. 2 times cosine theta minus cosine squared theta plus sine squared theta. Now this is the second one we did. Well, then they get the sine squared theta in terms of cosine squared theta, which is 1 minus cosine squared theta. So that gives you 2 times 2 cosine. They factored out the minus sign. Okay, why I'm not sure. We did too. 2 cosine squared theta from here. The minus sign went outside. Cosine theta minus cosine theta and minus 1 here because the minus went out front. Factor this and you get 2 cosine theta plus 1 times cosine theta minus 1, which is I think just what we got. And that happens when cosine theta is equal to minus 1/2 and cosine theta equal 1. It's minus 1/2 at 2/3 pi and 4/3 pi, which we got, and also at, and yuck, and it's 1 at 0. Okay, so, okay, is anyone else coming in or did that just pop up there? Okay, now, so those are the 3 possibilities for horizontal tangent lines. Okay, now, similarly, using x equal r cosine theta, you have x equal r cosine theta. I don't know why they wrote it twice. And then plug in what r is, 2 times 1 minus cosine theta times cosine theta. And that's, now this time they did multiply through like we did. Okay, 2 cosine theta minus 2 cosine squared theta. And that will be, when you take a derivative there, here, this will be minus 2 sine squared theta plus 4 cosine theta sine theta, which is exactly what we got. Then they factored out the 2 or minus 2, well, they only factored out 2 sine theta and then gave them this. And sine theta is equal to 0 at 0, and so the dx d theta is equal to 0. This one is at theta equal pi halves, equal 1/2, cosine theta equal 1/2, and that would be at your pi thirds and 5 pi thirds, which is what we got. Now I said equals 0 at 0, also equals 0 at pi. Sine of theta is 0 at pi 2, 0 pi, not 2 pi because that's not in your domain. Okay, from those results and from the graph shown here, you can conclude that the graph has horizontal tangents at 3 2 pi 2/3 pi, at 3 4/3 pi, and has vertical tangents at 1 pi thirds, at 1 5/3 pi, and 1 at 4 pi. Now, time out a moment here. They jumped the gun on you big time here. And here's why. You have to go back to your original function, which if I can find it here, yeah, here it is. R is equal to 2 times 1 minus cosine theta. Okay, you have to put in the theta for every one of those points that we were talking about. And they didn't show how they did that. So remember that, 2 times 1 minus cosine theta. Okay, so let's plug that in here. Oh, my internet connection is unstable, so I'm going to quit writing and talking until it comes back. Did I break up some in there?
Just a little bit.
Okay, well, I hope I'm back now, so that's fine. So let's see if I can write it down, if I can find it. R is equal to, do y'all remember? 2 times 1 minus cosine theta. I can't find my pen now. Come on back, pen. There you are. 1 minus cosine theta, was it? I have a good memory. It's just real short. Yeah, that's it. Okay, so when theta is equal to 2/3 pi, this would be 2 times 1 minus, and cosine of 2/3 pi. Oh boy, here we go again. That's a negative because you're over in the second quadrant, but you got a minus in front, so that makes it a plus. And the cosine is 2 plus 1/2, I think it is. Okay. All right. So this would be 2 times 3/2, and that would be 3. That's where they got this one. 3 2/3 pi. You plug back into your original equation to get what R is. You found out what theta is. 4/3 pi would give you the same thing because cosine of 4/3 pi is also 1/2. So that would give you that same thing. So that's why you have 3 4/3 pi. Okay, you plug back into the same thing. Let's see if I can do it here. R is equal to 2 times 1, was it minus, I have a good memory, it's just real short. Yeah, minus cosine theta. Okay, but now the theta is pi thirds. Well, cosine of pi thirds is again 1/2, but it's 1 minus 1/2. So this would be a 2 times 1/2, which is 1. And that's where this 1 comes from. Do the same thing for 5/3 pi. R is equal to 2 times 1 minus cosine of 5/3 pi. Well, 5/3 pi is also, cosine of 5/3 pi is also 1/2, and 1 minus 1/2 is 1/2. 2 times 1/2 is 1, so that's where that 1 comes from. Now, let's do the same thing for the pi, and you got R is equal to 2 times 1 minus cosine of pi. Okay, well, cosine of pi is minus 1, so that's going to be 1 minus a minus 1 is 1 plus 1 is 2, times 2 is 4, and that's where that 4 comes from. Okay, now the places where your x and your y were both 0 is right there. Okay, that's where it is, right there. And it kind of looks like you might have a horizontal tangent line being 0 there. It's hard to say. Okay, definitely you don't have a vertical. So you have to sort of exclude that point, but you can just throw that in as 0. When cosine is 0, this is 1. 1 minus 1 is 0. So you know you're starting your r right there. And when you come all the way around, it's back to 0 again. That's called a cardioid. And I think the reason for that, it kind of looks like a heart. If you stretch, I mean, not the Valentine's type hearts, your actual heart. That is that type of a curve. Okay? So that graph is called a cardioid. Okay. Note that both derivatives, dy dx, dy d theta and dx d theta were 0 when theta equals 0. And using that information alone, you do not know whether the graph has a horizontal or vertical tangent line at the pole. Hard to say. From the figure, you can see that the graph has a cusp at the pole, which is probably what you would expect because it's not smooth there. That cusp means it's not smooth. So theorem 1011 has important consequence. If the graph of r is equal to f of theta passes through a pole when theta is equal to alpha, and f prime at alpha is not equal to 0, then the formula dy dx simplifies as follows. Okay? Now, remember all these ifs in there. Dy dx would be this thing, which is this was our numerator from before, this was our denominator from before. They rearranged the order. Okay? Now, remember they said if it passes through the pole when theta is equal to alpha and f prime of theta is not 0. Okay? So they put in theta equal alpha everywhere here. Okay? And I'm trying to see where they got. Okay. Okay. For the life of me, I'm not quite seeing how they get rid of these. Um, was there something before they said? Let me back up and see if I'm forgetting something. Okay. Both the derivatives dy theta and dx theta are 0 at that point. So if, no, that wouldn't be it. I'm almost guessing they have this slide. No, they have it right. Okay. I know what they do from this step to that one. That's pretty obvious. If these are both zeros, what I'm having trouble figuring out is why they're equal to 0. They didn't say f of alpha is equal to 0, did they? Maybe that's it. Yeah, if your r is 0, then that is your F there. And that, I guess, has to be 0. So that must be it. I'm not totally convinced of it, but if they said if it passes through the pole, or yeah, there it is right there. It was on this page. Where is my, there it is. Okay, R is equal to alpha theta. If it passes through the pole, that means R is equal to 0, means alpha theta is equal to 0. So therefore, both of these are equal to 0. And that makes these zeros here. And you have sine alpha over cosine alpha, which is tangent alpha. Okay, so if it passes through the pole when theta is equal to alpha, then the tangent alpha. Okay, so the line theta equal alpha is a tangent to the graph at the pole, or at 0 alpha. Okay. Alright, so here's theorem 12.4. Tangent lines at the pole. If alpha theta is equal to alpha of alpha is equal to 0, and f prime of alpha is not equal to 0, then the line theta equal alpha is tangent to the at the pole to the graph of r is equal to alpha theta. Okay. So if alpha of alpha is 0 and f prime of alpha is not, then the and alpha of alpha would be the place where this is equal to 0. R is equal to 0. All right, that was too much of that one. Okay, let's do some of these special polar graphs. How are we doing on time? We go to 1:55, so we got a few minutes left. Let's look at a few special polar graphs. Several important types of graphs have equations that are simpler in polar form than in rectangular form. For example, the polar equation of a circle having a radius of a centered at the origin is simply r is equal to a. Now they didn't show that one, but that's pretty obvious. There'll just be a circle there. In xy coordinates, that would be x squared plus y squared is equal to a squared. So r is equal to a is simpler. Several other types of graphs have simpler equations in polar form. Here, this is called a limison, I guess is how you say that. R is equal to a plus or minus b cosine theta, or R is equal to a plus or minus b sine theta. Now this requires a and b both to be greater than 0. Can't be 0 and can't be negative. Okay, so in this one, the ratio of a to b is less than 1. So this number is less than b. Okay, a is less than b. Okay, for the ratio to be less than 1. That gives you this one. It gives you a cardioid if that ratio is equal to 1. And if you look back at what we had before, where was that cardioid? Yeah, your A and your B were both equal to 1, so that came up being a cardioid. Okay, now this one was backwards from the other one, but it's still a cardioid. If the ratio A over B is between 1 and 2, they call it a dimpled limison. Okay, if however A over B is greater than or equal to 2, then they call it a convex limison. Now what convex means is there is no place where the distance here gets any greater. Okay, you see the distance along this axis here is less than the distance along that. okay, because that's a little bit wider. So this is what basically like a convex lens. This one would be somewhat concave and convex. This, of course, has a pole there, and this is a limison with an inner loop on it when that ratio is less than 1. Now, why are these important? Beats me, okay? But these are some special polar graphs, okay? We've hit the cardioid, now we hit limisons with an inner loop, with a dimple, and convex, okay? And this is a limison, but it's a cardioid, heart-shaped limison. Now, more of these polar graphs, okay? Now, rose curves. You have end petals when n is odd. You have 2 end petals when n is even. That's what I was talking about before. So if your n is odd, then whatever your n is, that's how many petals you have. When the n is even, you have twice that many petals. And that's why before, if you go back, it wasn't on the slide set, but in the book, when it was a 2n or 2 theta, you came up with 4 petals, okay? So this is one when n is equal to 4, you wind up with 8 petals. N is equal to 5, you get 5 petals. N is equal to 2, you get 4 petals, okay? And so on. And you can always go with this. If n is odd, that's the number of petals you get. When n is even, you get twice the number of petals of n. All right, then circles and lemniscates. A circle is when r is equal to a cosine theta. And before we saw one r is equal to a sine theta. That's when it's set up here. A cosine theta, it sits over here. There's r sine theta here, just like we saw before. Here's a lemniscate with, it's in the form of r squared is equal to a squared times the sine of 2 theta. And this is a lemniscate r squared is equal to a squared cosine 2 theta. So the sine of 2 theta, let me see, I think someone had to leave. And it's almost time, isn't it? Well, not quite. We've got 6 minutes. A lemniscate, basically, they're not exactly petals, but they sort of look like that. When it's a sine, it's odd function. When it's a cosine, it's an even function. Okay? Same thing happening on the right as left. Opposites happening on the right from what's happening on the left. But those are both lemniscates. And that is the last example in 10.4. Okay? There are some concept check here on page 726. Homework exercises would be any of the odds 5 through 13. They're all at Calc Chat. 7's at Calc View. Any of the odds 15 to 23, they're all at Calc Chat. 17's at Calc View. Any of the odds 25 to 33, they're all at Calc Chat. 31's at Calc View. Any of the odds 35 to 43, they're all at Calc Chat. 37's at Calc View. Any of the odds 45 through 53, they're all at Calc Chat. 55 and or 57 are at Calc Chat. 59 and 61 are at Calc Chat. 63 is at Calc Chat and Calc View. 65 and 67 are at Calc Chat. 69 is at Calc Chat and Calc View. 71 is only at Calc Chat. The odds 73 to 79 are all at Calc Chat. 77 at Calc View. The odds 81 to 91 all at Calc Chat. 93, 95 are at Calc Chat. 97 and 99 should be at Calc Chat. 101 should be at Calc Chat. 103 and 105 should be at Calc Chat. 107 through 111 should be at Calc Chat. 113 and 115 are true false. They should be at Calc Chat. And then they have a little special project called Cassini Oval. So there's another potential paper topic. Who was Cassini that they're referring to here? How or why did he develop this? His name, by the way, was Giovanni Domenico Cassini. Okay. Now I know there's a Cassini that they named a space probe after, the Cassini-Huygens, I think it was, that the European Union sent up. I don't know if that's the same Cassini or not. But anyway, there's a potential paper topic. Okay, we're not going to do 10.5, nor, if there is a 10.6, we're not going to do, let me see. And we're not doing 10.6. Okay. However, thumb through those sections. If there's something you may need in the future, by all means pay attention to it. Okay. I don't know what your majors are, so I don't know what it would be, but also in thumbing through it, you will see potentially more potential paper topics. And I saw one, Johannes Kepler, is who he was, and Halley's Comet, there's another. So there's all sorts of potential paper topics there too. And that finishes chapter 10. The next thing we're going to is chapter 11, vectors and the geometry of space. Now, I can't recall if I put your test out there or not. Has anyone checked to see if I did? I know I have your test made up. I have your test. I think I put it out there. We've got 2 minutes. Let's just go and check. I believe it's there. Let me see if I can find it. Content, Google Chrome. There we are. Let's do weekly assignments and see if it's there. That would be under week 8 if it was. Let's see if it's there. Come on. Oh. You can't double click. You have to single click. There we go. Yeah, there it is. Chapters 9 and 10 test. So it's here at week 8. I guess I clicked on it, didn't realize there was. Here's the PDF version. Here's the Word version. If you can't read the Word file, use the PDF. If you can read the Word file, use whichever you want to. But not only is it there, I also put it, in case you didn't remember to look for it there, which to me is a bizarre kind of place to put it because you have so much to search through to make sure you get it right. I'll always put your test at, let me close up this one so it'll be easier to maneuver. I always put your test at the Blackboard messages. So if you click on there, there is the chapter 9 to 10 test. 2 copies of it. I put the Word file and the, I'll open that up for you and let you see. There's the Word file, there's the PDF version. That's just in case some of you can't open or read all the things on the Word file. I'm almost certain, I believe it was you, wasn't it, Cal, that back in the summer you weren't able to read some of the things I put in a Word file. The only thing I can figure on this computer they loaned me from the campus, it's a fairly new computer, they must have put a very recent version of Word out there, or a bizarre version or something, and not everybody's Word can read that. So that's why I put them both out there. So yeah, your test is already there. All right, any questions? I'm going to stop sharing. If there are no questions, oh, we lost, no, there's Kyle, he's still here. Okay, if there are no questions, I think it is time, yep, past time, so I'll see you again. Some of you I'll see in about half an hour, some of you I'll see tomorrow, same ones, and then we'll see all of you again on Wednesday. Good deal. Any questions? Okay. We'll begin on Wednesday with 11:1. All right. See you then.